Greetings, this is Mr. Garwood with our continuing video series on Calculus, second edition by Briggs, Cochran, and Gillette. This video is going to be the continuation and hopefully completion of section 3.2, and we're going to be looking at the idea of what does it mean to be differentiable at a point. Differentiability is really just a fancy word for derivatives. So what this really means is f is differentiable, which means the derivative exists at some value when x is a. There are three critical rules for this. Number one, f is continuous at a. And I really need you to know this definition, but just a quick reminder, that means that the limit as x goes to a from the left is the same as the limit as x goes to a from the right is the function value. And I'm hoping you remember if these two things are true, that means that there actually is a limit as x goes to a. Now, second rule, f has no corners at a, and we're going to talk about what that means graphically. And the third one is the slope at a is defined. Your book says this as there are not vertical slopes at a. What that means is we don't have something going perfectly straight up and down. So I want to run through a couple graphs real quick and just really highlight what this means. So looking here, we notice here there's a gap. There's clearly a gap here at a. And we could talk about, we're getting ready to talking about the idea that are the slopes the same as we come in from the left to the right. Love how I did that so you can see, like, are the slopes coming in the same way, or are they really whoppy where one's going up and one's going down? The big idea here is if there's a gap, I don't care anything else, the function is not is not differentiable there. In fact, if a function has a derivative at a point, that actually is a way of saying that the function is continuous at that point. So that is actually quite useful sometimes in some other areas. Now, Mr. Garwood, you talked about the idea of a corner, and I frankly have no idea what you're talking about. So here we go. Let's talk about what is going on with this idea of a corner. So I'm looking at figure 319, which is found in your book on page 119. And we've got a whole lot of lines here, and I think if I'll come in and I'll color code them a little bit, it's going to make your life a lot easier to see. So I'm going to color the actual function, f of x is that blue shaded area. And we're really interested here at this peak, this spot where the function changes. Now, what I then can say is, all right, what's the slope doing as I come from the left? And so as I come from the left, I've got a positive slope, and it's very obvious. Hey, look, there's the slope if I look at it from the left. But if I come at it from the right, that's the slope. And so what this is the corner. So this is what your book calls a corner. I have also heard it called a cusp. But the idea here is it's not smooth. One of my favorite rules for continuity is that if it's continuous, I can draw it without ever picking up my pen. One of my favorite rules for differentiability is I can draw it without stopping the pen. So if you notice here, for me to make this turn, I have to come up here, stop, and then change. Whereas and there's really not a good fluid way for me to perfectly follow this function without me having to stop first. I can kind of go, woo, but if you notice I come way off, it's really, really hard for me to stick to it. So this is a corner. The idea is if it's nice and smooth, I'm going to try and do this with my hands. If it's nice and smooth where they're doing the same thing, we're okay. But if I have a kink or a cusp or it changes, something weird's going on where it's not fluid, it's not smooth, then it's not differentiable. And that goes back to what we were doing originally in that first video from this section, where we look, there's very clearly, we're going back to the same video from our previous video, or the same picture, there's a corner here to here, it changes. From here to here, it changes. And so this function is not differentiable at -2 or at 0 because of this corner. That breaks that second rule we talked about. Now the last picture I want to talk about is the idea of this vertical slope. So we're looking here at the function of y equals the cubed root of x. And I'm going to argue that the cubed root of x does not have a derivative at 0. And let's talk about why. So I'm going to highlight in blue this function, this cubed root of x. And what's happening here, if I look at the derivative from the left, or the slope from the left, if I come in here, the slope is a perfectly vertical line. Well, the problem here is the derivative from the left is infinity, and equally so, the derivative from the right is infinity. It has a slope of infinity, and the problem here is we're saying that's undefined. Remember, we want to have a situation of, hey, look, the slope here should be something that I can graph on a function. Well, we can't graph infinity on a function. And so we say the function is undefined at that point. So here we're going to have to say that the derivative is undefined at 0 because that slope is infinite. So where does that leave us? Well, that leaves us with the idea of, for me to have a derivative, I have to have 3 things to be true. Number 1, f must be continuous at that point, which means the derivative, or this one will work. This is slightly different. This is obviously my second attempt at the video. Let's try this one. F is differentiable at a point A if it's continuous at A, which means the limits from the left and the right of that function are the same, as well as the function value. F doesn't have a corner. It doesn't have a weird kink that is doing weird things, and I cannot have a perfectly vertical slope. I hope you found this video useful, and I wish you luck in the coming semester.